All right, so for those of you who showed up, good on you. We'll kind of do some housekeeping stuff, get out of the way, and then we'll jump into material, kind of where we left off. I realize I'm sure other professors are much kinder. I guess they gave you extra credit, things like that. We have your econ majors, the value you must have thought that the marginal benefit of attending today was greater than the marginal cost, right? So it's up to you. Any given class period that might change depending on what is important to you. I'll have this kind of recording. In fact, today I'll probably be nice, and I'll probably record what's on the dot cam. We don't have any quizzes or anything today, so I would expect one likely on Thursday. Right, so that might be good for to make sure you're aware of that. So in fact, let me just go over here. So we'll have this recording as we kind of go, and we will pick up where we left off. So I'm going to try to trying to organize my Canvas pages a little bit better. I'm still learning tools along the way. So I'm going to start to try to section out what we do every week. So kind of here's all our class files that you might need to download and we might use in Stata or other programs. I'll kind of try to group problem sets with a data set as well as that first problem set that should be out there. It's not due for a while. I mentioned after last week, you can kind of start on those first few questions, getting used to working with Stata on your device. If you're still having questions or not able to get that working, I would strongly suggest you stopping by my office hours tomorrow or on Friday. So I posted an announcement up at the end of last week. So I'll have a couple more office hours on Wednesday. So when did I have these? Oh, where is it at? Oh, so I put them on Friday. I expect another announcement. I'll probably be around my office most of the day tomorrow. I just kind of have to carve out maybe an additional hour or so that I can guarantee I'm going to be there if you stop by. So we really want to make sure we're getting Stata working so we can start working on that problem set so it doesn't, it's got 9 days to kind of work on that. I don't want you coming to me the 28th and so I still can't get Stata to work, right? You should be making sure you can open that data set for the first problem set, start working on it. If not, this is a good thing to come by my office hours to get help with, okay? So I'll be around most of the day tomorrow. The usual office hours, 9:30 to 10:30. Since I canceled my office hours yesterday, since it was a holiday for the university, for MLK Day, and then also a big event for the university last night. I'll kind of move. I have those office hours on Friday, but I'll also be available tomorrow. So look for an announcement up for that. So I use this announcement kind of tool in Canvas to kind of post things that maybe I haven't mentioned in class or to reiterate things that I have said in class. So today we'll start working with these module 2 slides. So some of them are kind of repeated from what I had in the module 1 slides, just kind of where we left off, to kind of section out. I also updated it before class, but if for some reason you downloaded it last week, I updated this group data. It had one error in it, which I'll mention kind of once we get there. Other than that, I would start working on that problem set early. The other thing to kind of mention is I put up those practice problems for that first quiz. I'll post this after class on Thursday. We'll likely have worked through everything you need for that quiz. And that'll be due kind of the following week at the end of the day, Friday. So you have about a week to work on that. You can start looking at those practice problems kind of early. We've covered some of it. Some of it we won't get through until the end of this week. Okay. So quiz 1, we'll kind of post up after class on Thursday. You've already got that problem set you can start working on. Yeah.
The quiz is due the following Friday?
Yeah. Okay. Yep. So you have about a week. Like I said, you can start reviewing the practice problems now, but once it's posted, you'll have about a week. Any point you want to get on, once you start it, you'll have 60 minutes to complete it. I'd probably, suggest maybe not doing it right after class Thursday. Spend a little time reviewing for it, but you'll have that whole next week, kind of whatever works for your schedule, the best time where you can sit down and kind of focus on taking that. Okay. And they're pretty short, 10 to 12 questions. But you'll have 60 minutes once you start.
Is it usually choice, short answer?
Kind of a combination, right? So there's some numerical, as we progress throughout the semester, a lot more it's going to be numerical response, but there'll be some multiple choice. There might be some select all that apply. I'll kind of indicate, be very clear about what type of question it is. Like if it's a select all that apply, there's not just one answer because they look similar, right? Multiple choice and select all that apply. For the most part, it'll be like numerical response as we kind of start to work into the semester. Yep.
Thank you.
All right. Any other housekeeping questions before we get going here? Okay. So Where did we leave off? All right. So we started talking about kind of this relationship between two variables. And we said we had this measure of the covariance, which told us something about, to not be so technical, but do these two variables tend to be on the same side of the mean or opposite sides, right? So if they're on opposite sides, we ended up with a negative covariance, or meant that when one variable was high, the other tended to be lower, right? Or vice versa. We then kind of looked at, okay, how do I take that covariance, which if I'm taking two variables, right, the deviation of x from its mean and the deviation of y from its mean, well, if I have different units, I end up with things like student points, or if I'm looking at the relationship between height and weight, inch pounds, like what the hell is that? We don't really have any way to interpret it. We also want to compare the relationship of different types of variables, right? The relationship between height and weight compared to the relationship between the number of students in a class and the number of points on a standardized test score, right? So there we would kind of create this correlation coefficient, which takes the covariance, divides it by the standard deviation of both variables. That gives us this nice unitless measure, right? So that's kind of where we left off. We said we could look at like a scatter plot. For right now, if I was to try to draw a line that best fit this data, it's not completely accurate, but for right now, that's the best way to kind of think about this correlation coefficient. If it's positive, we'd have a line that kind of was upward sloping or has a positive slope. If it's a negative correlation coefficient, we'll end up with this line of best fit that's kind of downward sloping. Okay. So we looked at how we created scatter plots in this data. That was kind of how we left off. So I've got an example in Excel that we'll kind of work through. So go to here. I'm going to open this grouped data covariance example. So sometimes we'll have continuous data. Sometimes we'll have group data. So this is probably, we start to transition after these first couple weeks, more from like looking at Excel to just looking at Stata. But for right now, since you're not as familiar with that, we'll kind of start out in Excel. So I have all this data for every state. I think I just limited it to one time period here, but I've got a whole bunch of years. So we can look at a state's population. We can look at whether or not medical marijuana was legalized, and we have the violent crime rate in that state. Okay. So if I had the continuous data, right, I just have every single state here, how would I find kind of the mean? I would simply look at that violent crime rate for every state, add them all up, and divide by the number of states, or 50. I think DC or District of Columbia might be in here, so maybe it's 51, but same idea. Same kind of idea. How would I find the average of these states of whether or not they had medical marijuana legalized? So if I have a 1-0 variable, or what we'll end up calling a dummy variable, right? It's just kind of a weird name, but right, it just means that it's a 1 if this is true, 0 if not. What would the mean of a 1-0 variable actually tell me? So when thinking about medical marijuana being legalized, what does the average of that variable actually tell me?
Percentage of states that have legal.
Close. Not the percentage, but the probability, right? Now we can work back and forth, right? If the probability is 0.42, that means what percent of the states had medical marijuana legalized? 42%, right? We can kind of move between probabilities and percentages by simply multiplying by 100. Or if we have the percentage, how do I get the probability? Divide by 100. So I've got, looks like I don't have DC here because I can find the number of observations. Now this is things I won't quiz you on or expect you to know, but we have like these mean functions in Excel. We can do means in Stata. We started to kind of look at that last class, and we'll kind of revisit that later on today. We can find the mean of that medical marijuana variable. And then here, I can just count the number of observations I had in that range, okay? So that's kind of nice and easy with continuous data. I've got the mean of both variables. So let's say someone told me that mean, but I couldn't actually observe the data. All they gave me, right? So if I had the continuous data, we also have some nice functions, which are, I can find the covariance, right? This goes through every single observation. It takes that state's value for the violent crime rate, subtracts the mean, multiplies that by the difference of whether or not they had medical marijuana legalized and the difference between that mean. It does that for every single observation, adds them all up. That's our covariance. Okay. Now, our correlation coefficient, we would have a built-in function, but what else could I do here? If I know the covariance, I could also find, oops, see if I can remember, here it is. I could find the standard deviation of my violent crime rate variable by simply selecting all the violent crime rates, right? So I don't have to do this by hand. In fact, most of the calculations we're going to do this, I'm not going to expect you to take 50 observations of the cat. It's going to take a while, all right? Now I could also take the standard deviation of that medical marijuana variable. So this is where, just like in Excel, in Stata, we can do these things. Sometimes there's a function. So here there was a correlation coefficient function that calculated that correlation coefficient between those two variables for us. We don't always have to rely on these built-in functions. If we want to, we can even prove to ourselves that hopefully, if I wanted to calculate that correlation coefficient, it should be that covariance that I calculated divided by what did we just have in that slide, divided by each standard deviation. So the standard deviation of my violent crime rate times the standard deviation of that medical marijuana variable. Hopefully when I hit enter here, I get the exact same value as that built-in correlation coefficient function. So this is very similar in Stata. Sometimes we'll have functions that do things for us, but if we have, you know, a formula behind that, we can often do it ourselves, right? And when it comes to like grading, in fact, after the first problem set, I'll put out a solutions file so you can go back and kind of see what you got right or wrong. Sometimes that solution file will have multiple ways of doing the same thing because there often are, right? And this will make a little more sense as we start to work through more examples, but here's kind of an example of that in Excel. There's a built-in function to find the correlation coefficient, or we know that the correlation coefficient is the covariance divided by each variable standard deviation. Okay. So that's nice if we have the continuous data. Let's assume instead we have this group data. Okay. So I don't know what state has medical marijuana legalized. I don't know what their violent crime rates are, but I have kind of this 2x2 matrix that tells me if I were to select a state at random, the probability that it has medical marijuana legalized is 0.42, which means what proportion of the states must have it not legalized? Well, they either have it legalized or not, so that should always add up to a probability of 1 or 100%. So I know automatically, hopefully, that this is 0.58. Sure enough, if I kind of sum these up, right, count the number of zeros and the number of ones, divide by 50 states, that's what was giving me these values. Now, I've got some formulas behind the scenes here. Don't worry about that. Let's just say I told you that the proportion of states that have above kind of this mean violent crime rates was 0.46. The proportion that has below is 0.54. So I don't have maybe above or below, but I have specific values to what those are. So, you know, every state, even though it's above the average violent crime rate, they can vary, right? So I'm just going to use a value for this group of 400, and then I'm going to use a value for this group of 300, okay? So if I'm thinking about when I'm calculating the means here, if we have grouped data, how would I calculate a mean, okay? It's going to be the probability that this variable X takes on a certain value. So let's just do the medical marijuana one. That might be a little bit easier. So the probability that that medical marijuana variable is equal to 1 times kind of what proportion of those states have that value equal to 1. Or sorry, the proportion of states that have, or the probability that states have that variable equal to 1 times what's the value of X if they have it legalized will just be 1. So for these dummy variables, it's a little bit easier, right? And then what would I need to add to that? Well, what are the other outcomes I could see for that variable? The probability it's equal to 0 times the value of X if it's equal to 0. So for that medical marijuana variable, it's not as difficult. It's not really as complicated because anything times 0 is 0. So if I know the proportion of states that has medical marijuana legalized is 0.42, what's the mean of that medical marijuana variable? It's just 0.42 times 1, right? Now I could plug these values in, but once again, anything times 0 would be 0, okay? Now, if I was doing the violent crime rate variable, here I've got group data, right? So I know that truly I could see any violent crime rate between like 0 and I don't know what the highest value is, but let's just say it's like 1,000 or something like that, right? Well, I would take the probability that I saw the value of that first group, which I said was 400, I think was the value I have in the Excel file. So the probability it's equal to 400 times, right, the probability that it's equal to 400, right? The value times the probability. Now, in this case, the second value or the second group I have is what's the probability it's equal to 300 or kind of was below that mean. And we were giving that specific value of 300. So here we have a little bit more work to do, right? Now, why am I using the value of 400 and 300? This is just because I don't have the actual continuous data. That's what was given to me grouped, right? I know I have an above and below the kind of mean group. The values I'm using for those groups are 400 and 300. Huh?
So over there we have like two different sections where I talk
Hmm?
about the means above 400 and for one section the means below 300.
So this is, think of it this way. I know I have some states that have above the average or above the mean. Now, what value am I going to use for those groups? Here, we already calculated the mean. We know it's 346. So all of these are different, right? Some of them are well above 346. Some of them are just barely above that. So the value we're going to use for that group is just 400, right? Now, where did that come from? That was just the way the data was reported, right? That on average, we're going to treat this group as though they have a violent crime rate of 400. We don't truly know what that value is going to be. In fact, we don't want group data. Ideally, we have the continuous data. We don't have to worry about this. But in some situations, we will have group data, okay? Same kind of idea. There's states that have below the mean. Well, the mean is 346. What value we're going to use for that group? Something that's below, we'll just use 300. Technically, we could have chose, 380 and 320 or two different values on either side of the mean, okay? So with that group data, right, how was I calculating kind of the mean here? We would kind of go through those, how I kind of wrote it down, right? So we can also do kind of the standard deviation, right? Now, I shorthanded this a little bit, right? So I think about there's 4 different types of groups here. One, they have medical marijuana legalized and they have above the mean violent crime rate. They have medical marijuana legalized and have below. So and then the other combination. So there's really 4 different groups, okay? So if I wanted to know kind of the standard deviation of both of these, right? Or I would eventually could find the covariance. Well, the standard deviation is simply going to be, I take each possible value for that violent crime rate variable. So I've got 400 and 300. I would kind of think about what's the deviation of that value from the mean. So 400 minus this mean of about, and I'm kind of cheating here a little bit, but I'm just rounding it. So the deviation between that and 346. I would then square that value and then add to it the deviation of the other group from the mean, kind of add those up and take the square root, right? Now, I did kind of leave out one thing here. What should I technically be doing here? So I don't just take the deviation squared. I would take that deviation squared and multiply it by the likelihood I see that deviation, right? So here I would say, okay, here's that deviation squared. I want to multiply that by the likelihood I see 400, which would be this total right here. And then for the other group, what's the probability I see 300? 0.54. Okay. So this is how I would use the group data to come up with that standard deviation for my violent crime rate variable. Okay. Now, for the medical marijuana variable, it's a little bit easier, right? Because I just have 1 and 0. But now here, unlike the mean, something's not getting multiplied by 0 because even when I see 0, 0 is going to be some deviation from that mean. So once again, I think it ends up being exactly right here, so I don't have to round. But here I could see medical marijuana be 1. It's deviation from that mean of 0.42 squared times the probability I see that variable be equal to 1. And then add to that the probability I see it be equal to 0 times that deviation squared. And then why am I taking the square root of that? When I take the deviations from the mean squared, multiply it by the probability I see that deviation, if I add those up, that gives me the variance. To go from a variance to a standard deviation, all we do is take the square root. So that's why I'm adding that in there. Once we have those standard deviations, the other thing I need to calculate a correlation coefficient is that covariance. Now, here's where it gets much more complicated, right? Because when I'm looking at the covariance, I need to look at what are all the possible combinations of these two variables. So for the very first one, this is that I see medical marijuana be legalized and the group of that violent crime rate that has above the mean, which we were using the value of 400. So the deviation of the violent crime rate from the mean times the deviation of the medical marijuana variable from its mean, right? That was kind of our covariance. Now, when I multiply those by each other, when I have group data, I then need to multiply those deviations by the probability I see both of them occur. So the probability if I selected a state at random that they have this above mean value of 400 and they have medical marijuana legalized, the probability I was in that group was 0.22, which is why I didn't use a cell reference here. I'm using the actual numbers, so it's a little bit easier to kind of connect. We just have a bunch of cell references. It gets kind of trickier to see. Now, what's the other possible combination I have? That they have below the mean, or this value of 300, but they still have medical marijuana legalized. So the deviation of the medical marijuana variable would be 1 minus the mean times the deviation of this below mean group, 300, from its mean. I then need to take those two deviations multiplied by what's the likelihood I see those two deviations at the same time? The probability that I saw that occur in the data, which here was 0.2. I then do that for the other two possible combinations of these variables. I then add them all up. Okay. So a little bit more work to calculate that covariance. Okay. Now, if I'm doing this by hand, right, if I didn't do the group data, what would I be doing? You can kind of almost think about this here. I would have to go through every single observation, take the deviation of the X variable medical marijuana from its mean, multiply that by the deviation of the Y variable violent crime rate from its mean, do that for every single observation, add them all up. That would give me my covariance. Now, that isn't going to quite be the same as if I'm doing this with group data, right? There will be some discrepancies, right? Whether I have continuous or group data, I should still end up with approximately the same value, or at least the same sign, right? Which is really ultimately what I care about. Are these two variables on the same side of the mean, or do they tend to be on opposite sides? So if I calculated that covariance, and I had the group data standard deviations, how would I calculate that correlation coefficient? It's simply that covariance divided by each standard deviation. So you'll notice, if I do this using group data, do I get the exact same value as if I was using the continuous data? No, not quite. They're close, right? They're both positive. It won't be that I get a different sign, but they are going to be slightly different values. And that's really because we can make more accurate statements if we have continuous data as opposed to group data. It's just that sometimes the data sets we have are limited. In fact, most of the time, if you want stuff from the government, they're not giving you individual level data. You might be able to get down to the county, but it's still going to be somewhat grouped, right? So we need to be able to still calculate standard deviations, calculate means, calculate covariances using group data, which, what's the kind of added wrinkle? We have to start using those probabilities, okay? Any questions? I know I worked through this kind of quickly. This should be somewhat review. Hopefully you did something like this in your stats courses, okay? So that was kind of our correlation covariance. We started talking about at the end of last class. This kind of rounds out that discussion. Okay? So the next thing that we're going to talk about is hopefully once again review, which is I can also look at conditional distributions, right? So I introduced the idea of distributions last class, which is essentially I know that some values, even though I can calculate the mean, if I select any one value at random, more often than not, most of those values will be somewhat close to the mean. And then as I move further from that mean, what happens to the probability I see values further from the mean? That probability starts to decrease, right? Unless I have some really weird distributions, more often than not, if we have large enough sample sizes, we'll see if we remember this from our old stats. What do most distributions, if we have large enough sample sizes, start to get close to? What is the Z table for? Standard normal distributions. It won't be standardly normal, but we often see when we get large enough data sets, most variables look normally distributed, right? Then in order to use the Z tables, we need to somehow standardize these variables, okay? So that's where we're moving. But any distribution we have could look different if we start to condition on things. Okay? So let's say I have this variable y and I'm interested in its distribution, but conditional on some other variable being equal to a specific value. So we can think of these as group means. I think the example I have here, right? And this will hopefully somewhat make sense. So if I have a standardized math score, and then I have what the parental education is in terms of years. So if I condition and say, look, I only want to look at the expected value or the mean of this math score if the parents both here, I guess, at the highest education level of the parent was 16, basically that had a college degree. So what do you think is likely true about the children of someone who has higher education compared to those that don't? Their kids' math scores or standard test scores tend to be higher. So notice as we condition on a higher level of education from the parents, what happens to the mean of that math score? It's a little bit higher. So not only do the distributions change, but the means themselves change. I think this makes sense. So I could then think about what's the value of my parents having a college degree for the kids. Well, just the difference between that mean if they have a degree versus if they don't. Now, let's assume these values are close, but let's assume that when I calculate these means, regardless of if the parents had 12 or 16 years of education, that I find no difference. What is that telling me? That's telling me that regardless of what the parental education is, the performance on this math score for the children tends to be the same, or essentially, it doesn't depend on their parents' level of education, right? In fact, if we look at this, there is like, it's because we're not controlling for other factors, but if we can control for a bunch of other factors, it doesn't matter near as much that your parents went to college or if they didn't, right? It's more about your own specific overall kind of intellectual ability, right? And we might see that these are what we call independent events. That even when I condition on this other variable, the mean doesn't tend to be different. So I'll give you an example of independent events. Let's say I still am interested in this math score and what its mean is. If instead of conditioning on parental education, let's say I want to think about what is the expected value or what is the mean. If I can get a marker that works. There we go. So what's the expected value of this math score if the height of the individual is, I don't know, they're 6 feet tall, compared to the expected value of that math score, and I'm using inches here. If their height is, I don't know, let's say they're, 5'8", so we'll do 68 inches. If I condition on someone's height, do you think that produces a different mean in the overall math score? I mean, there might be, I don't know enough about biology probably to be, but from what I know, your height has nothing to do with your intellectual ability, right? Maybe there's like a convoluted story with like if you had access to higher nutrition foods, that's good for your brain and it's also maybe cause you to, but more than likely, these are going to produce the exact same mean, I don't know, they're both 350. We would say that height and math scores are independent events. Doesn't matter if I condition on your height, the expected value of your math score is still the same. Right? There's no differences in the expected value of that math score for people of different heights. Right? So I'll kind of use a weird extreme example to kind of make this point of independent events. Okay. Now, parental education, I would imagine there probably is some relationship there. Like if your parents are more highly educated, they can help you navigate the college scene, admissions and things like that. And so we would see that there might be a difference in those means, or they're not independent events, right? They depend on each other. So if they depend on each other, our covariance is going to be something other than 0. If they're independent events, what would that covariance likely be? 0, right? Or the correlation coefficient, if that's just the covariance divided by standard deviations, our correlation coefficient would also be 0. Okay. So this is the idea of kind of conditional distributions, right? Or conditional means. We can take it a step further. Yeah.
When you did your on the paper, do you mean to put that because they're independent events, the answer would be the mean of y, not the mean of x?
It doesn't matter. I think the way, sorry, you're right. The way I wrote it in the slides, I think I had this was y and this was x. It doesn't matter if I called this x and this y. I'm just looking at two different variables. But yeah, sorry. If you want to line this up more with the slides, I think I had this is y, this is x. So technically I should have been saying the expected value y. So thank you for calling me out on that, right? It ultimately doesn't matter because we're just using, right? We could do q and z here, right? It's just whatever variable we're looking at. But yes, the expected value of that first variable is what we're looking at, kind of thinking about as the mean. So I think the other example that I then had, let me see if I'm remembering this right. Yeah, okay. So what if I could think about these expected values, but this is just the mean, right? So let's say I have this distribution and I'm thinking about kind of starting salary for an individual, okay? Let's say this black line represents, this is maybe self-important, but someone that has not taken 371, all right? That hasn't taken an econometrics course, right? Okay, well, we're going to have some mean, and just so that we don't get confused with X and Y here, right? We're looking at the mean starting salary, but this is a conditional mean. This is for someone that hasn't taken 371. So you could almost think about this as, what is the expected salary for someone where that E371, they haven't taken it, right? Now, what do you think's likely true? Hopefully, if this class has any value added, right? If I was then thinking about the expected starting salary of someone coming out of college, and they have some level of statistical understanding equivalent to 371. They're better able to work with data. They've started to work with this program where they can deal with large data sets. You think they're more or less attractive to a company? More attractive. Every company is working with data here, right? That's how you get a competitive advantage on other companies. And so if I have those tools, if I have more value to a company, are they going to be paying me more or less? More. So I would expect this mean kind of starting salary for someone who has taken 371 is likely going to be higher, which means that extremely low starting salaries are going to be even less likely than for the group that hasn't taken it. And extremely high values are going to be much more likely, right? So not only will these conditional statements, conditioning on certain groups, not only will it shift the mean, it's likely going to shift the entire distribution, right? It doesn't just increase the average, it could decrease the probability we see small values and increase the likelihood we see extremely large values. About the distributions? Yeah, so when we condition on another variable, it likely isn't just going to change the mean, it's going to shift the entire distribution, right? And here we could almost think about it, let's just assume starting salary is fairly normally distributed. Well, if I shift the mean and they're both normally distributed, when I shift the mean, I would inherently have to be shifting the entire distribution, right? So that means that when the mean is higher, lower values are going to be less likely, higher values are going to be more likely. Because although we don't often, I might get lazy and I don't kind of write what's on my y-axis, when I'm looking at distributions, what's on my y-axis? So these different values, the y-axis is telling me the probability that I see that variable, take on some specific value, okay? So if I have a higher mean, shift the distribution to the right, the probability I see lower starting salaries, even lower, probability I see higher starting salaries, even higher, Okay. Hopefully this is true about 371, right? Or you could even think about this as like a college degree. Okay. Any questions on this idea before we keep moving here? Okay. All right. So okay. So I mentioned this already a little bit earlier, but for most variables, if we can get large enough data sets, they typically tend to be normally distributed. That's not always the case. We can look at some examples where it's not, but we're going to be dealing with the normal distribution a lot this semester. Okay. So if we have a truly normally distributed variable, what that means is it's a symmetric distribution. And what is it symmetric around? Well, I don't think I had, let's see, did I have it here? There we go. It'll be symmetric around the mean. Okay. So what it's symmetric, what'll end up being true is the mean will be the same as the median, right? Because the median is going to be the value that happens most often, or essentially the highest point of that distribution, whatever X value that tends to be. Okay. Now we can have different normal distributions. So in fact, intellectual ability measured by IQ is fairly normally distributed, right? It's pretty symmetric, right? Now height, most biological markers tend to be normally distributed. So height is also normally distributed. But the values of height are much smaller than how we measure IQ, right? So each normal distribution will be defined by its mean and its variance. In fact, I think I'm getting a little bit ahead of myself in the slides here, but sometimes I think it's helpful to see these things drawn out. So I already really had one here where we had two what looked like symmetric normal distributions, but one was higher than the other. Now, the normal distribution is defined by that mean. The mean will shift it to the left or the right, right? Height has lower values than IQ, so we would have like a normal distribution more to the left. IQ would be more to the right. Now, let's say instead I was looking at, what's a good variable to get at this? So if I look at different countries, like developed versus developing countries, what'll end up being true is, so if I think about something like the US, right? We tend to have, most people have kind of the similar resources available to them. So I'll just use the US here. So we might have a normal distribution, right? Now, how much the data varies from that mean, that should be represented by what stat? How much the data varies would be our variance, okay? So let's just to put a number to it, let's say the variance in the US is 100, okay? If I have a different country that's less developed, or that where we have kind of some groups have really high levels of resources available to them, but some groups are treated disproportionately negative by that country, I might have a more spread out distribution. So it could be, call this kind of less developed, that maybe they have the same mean. There is just some inherent IQ level that we're all born with, right? However, when we have different resources available to us, some of us are able to get higher kind of, increase our intellectual ability. Whereas if some of us don't have as many food resources, some of us are going to end up kind of on the lower end. So in these less developed countries, maybe it's still a normal distribution, but the variance might be much higher. So it's still symmetric, right? It's still a normal distribution, but it's going to have more variance, which is going to look like a flatter distribution. So the higher the variance, the lower, I shouldn't say lower, but like the more squished the distribution looks like, right? It's much more likely in these less developed countries that some people don't have access to things that allow them to kind of increase their intellectual ability. And there's also groups that have much more resources available to them, right? It's kind of an unequal society. I'm kind of, not choosing any one country. I'm making a pretty large blanket statement here, but this is just kind of I sometimes try to think of these off the cuff examples that, we could think about this like as a more macroeconomic kind of example here. Okay. So the higher the variance, the more like squished that normal distribution is, right? The more variation that we see, the higher the likelihood we see extremely low and extremely high values. So every normal distribution is defined by its mean that shifts it to the left or to the right. Here, even if we have the same mean, the other thing that defines a normal distribution is its variance, how spread out that distribution is going to be or how narrow it is. In fact, you could imagine like that's still a normal distribution, but the variance is very, very small, right? Everything is centered kind of around that mean, okay? Any questions on this idea? Okay. So where are we moving here? There we go. So, the mean kind of shifts these distributions to the left or the right, even if they're all kind of the same normal distribution. And then we had that variance is going to make it more peaked or kind of more squished. I'm using very non-technical terms here, right? But these kind of higher variances, we're going to get a much more spread out distribution, right? Or another way that we might see this is if it's more squished, and I said the probability of seeing high and low values is higher, we would say it has fatter tails, right? That might be another way we kind of we talk about these distributions. Instead of saying squished or peaked, fatter or skinnier tails. That's just the kind of terminology that we'll see used in stats. Is this hopefully sounding somewhat familiar from like 370? So if we're just looking at a visual depiction, who has a higher mean height? We might know this one off the top of our head, but if we were to kind of separate this by gender, male, female, who has a higher on average or a higher mean? These are two conditional distributions. We've conditioned on gender. Who has the higher expected value or the higher mean? Well, where is kind of the peak of that distribution? It's a little bit higher for males. Right? The mean of that distribution is a little bit more to the right. Now, which of these heights tends to have a higher variance? It's going to be the one that is a little bit more kind of counterintuitive, but it's a little bit more squished. The tails are fatter. It's more spread out. So this is actually true about most things in biology, from my limited understanding, is that males tend to just have wider distributions. There's much more variation in the males of every species than there is of females. Once again, I don't know the biological reason behind why, but I do know that from a statistical standpoint, right? It's something about testosterone creates more variance than estrogen, and that's why we see this. Okay. But we can get that just from looking at the visual, right? The male distribution is shifted to the right, has a higher mean. It tends to be a little bit more squished or have fatter tails, so we know that it has a higher variance, okay? Any questions on this idea? Okay. All right. So when we're thinking about distributions, I said the y-axis is the probability, right? So if I want to think about this, I can kind of use maybe this height example just to kind of get this across. If I have a normally distributed variable, if I choose a specific value, the area under the curve, I can almost think about this. I'd be saying, okay, what's the probability that someone is 59 inches tall? What's the probability that they're 59.001? What's the probability they're 59.002? Right? I could do this for like every kind of infinitesimally small value, and the y value is telling me the probability I see that number. So if I were to choose like 63, what's the probability if I selected someone at random that their height would be less than 63? What would be the probability of every single possible value below it added up, or essentially this area under the curve? Right? So the probability I see 63 or anything below it is just everything to the left of that value, but under that distribution or under that curve. So if I think about what's the probability if I select someone at random, I don't know, who's the tallest person in the world? I think it wasn't Woodrow or Robert Wood, something like that. It was like 8 foot, something crazy. Let's say if I select someone at random, what's the probability they're under 12 feet tall? If I select anyone in the world at random, what's the likelihood or the probability they're under 12 feet tall? There's a 100% chance. Or if I choose the highest possible value for height, what would that be? Add up the probability of every single value below it. So the area under our entire distribution should always be 1. right? These are probabilities. Or a probability of 1 would be 100%. Okay? So when we're thinking about the area under this curve, it should always be 100% or a probability of 1. Now, what ends up being true about a normal distribution, and we'll kind of see where this comes from, but if I go 1 standard deviation to the left and 1 standard deviation to the right, or above and below that mean, the probability that if I select one person or one observation at random, it'll always be about a 68% chance I see something within 1 standard deviation above and below the mean. Now, where that comes from is we have a very specific, let's see if I skip ahead here. Did I put it in the, I think I didn't, just to not confuse you. So there is a, there's an actual function to the normal distribution. And if we were to take that function and integrate it, what we'll see is when we integrate that function, the likelihood or the probability of the area under the curve between 1 standard deviation above and below will always be 0.68 or about 68%. Okay? Now, we're not going to like do the integration. That's not what we're focused on, but we're going to use this kind of moving forward. And then if I were to go out 2 standard deviations to the left and the right, what would happen to the area under the curve, but between those 2 values? Well, if I just go out 2 standard deviations to the left and the right, the area under that curve is going to get larger, right? Or if you just think intuitively, what's the probability if I select one observation at random, probability it's between 1 standard deviation of the mean is going to be less than the probability it's within 2 standard deviations. And then that's going to be less than the probability I see it within 3 standard deviations, right? As I kind of go further and further out, this probability starts to increase. In fact, if I go from 1 to 2 standard deviation, it goes from about a 68% chance to about a 95% chance, right? And then if I go out 3 standard deviations, I'm already up to almost 100%, right? If I select an observation at random, it's almost a guarantee that it's going to be within 3 standard deviations of the mean, okay? Once again, hopefully this is starting to look similar to what maybe you talked about in your stats course. Starts with a C, CI, confidence intervals, right? This is very similar, it's related to that concept, okay? So we're going to use these normal distributions, and they're defined by their mean and their variance. So a lot of times how we'll see this written is this variable is normally distributed, capital N. Here's its mean, here's its variance, okay? We're also going to have a special case of these normal distributions, which we call the standard normal distributions. We can actually take any normally distributed variable and turn it into a standard normally distributed variable. So how would we do that? Well, if the standard normal distribution has a mean of 0 and a variance of 1, if I know the mean, if I take every observation from that data set and I subtract the mean, what will my new average be? 0. Right? If I calculate the mean, I then subtract that from every observation, and we'll see this in Stata, I think we'll get there today, we would have a new mean of 0. Now, if I divide by the standard deviation of the data, it's not as clear, but what that ends up with, it's going to give me a new variance of 1. So we would call this standardizing a variable. Once I know a variable is normally distributed, I can turn it into a standardized variable, which will have a standard normal distribution by subtracting the mean and dividing by the standard deviation. This should also be something that hopefully you kind of remember from 370. Once I subtract the mean divided by the standard deviation, I now have z-scores, right? Or a standard normal distribution, okay? So what do I want to say here? Basically, if I standardize this variable, the distribution of these z-scores will always be a mean of 0 and will always have a standard deviation of 1. Now, if I have a standard deviation of 1, how would I go from a standard deviation to a variance? We said before, if I have a variance, how do I get the standard deviation? I simply take the square root. So if I want to go from a standard deviation to a variance, I would square it. What's this? If I square 1, 1 times 1 is 1. So a standard normal distribution, the variance is the exact same as the standard deviation. Okay. So we've got our z-scores. I've kind of already mentioned this. We'll subtract the mean, divide by the standard deviation to turn any normally distributed variable into a standard normal distribution. Okay. All right, let's see what I want to say here. So we've got some standard. I want to do some work in Stata before we leave today. So we're going to kind of pick up here. We'll probably touch on this next class. I'll kind of walk through a little bit more of this, but we're going to take a look at how we, whoops, there we go, standardize variables in Stata. So let me see here. We're going to open up Stata, open up the do file editor. So I did this ahead of class just to kind of remind us. Once I have this open from IU Anywhere, I'm going to go up this little notepad, has like a little pencil next to it. I'm going to go to File, Open. I'm going to go to my OneDrive down here. Whatever folder I've created, once again, for you guys, I wouldn't do all these subfolders. I would just create one file or a folder where I drop all the files. We're going to use that same review of statistics do file that I was using last class. Okay, so I'm going to open this up. We kind of skipped through all of this stuff. We started looking at means, medians, just kind of scatter plots. So I'm going to go back to this line 21. Okay. So I said last class, one thing that's helpful, if you keep dragging and dropping the files into the same folder, your file path will never change. So for me, I'm doing subfolders. I make my life a little bit harder. Mine will change week to week. But this is where you would take my file path and just simply put whatever yours is. So I'm hoping, so if I just copy this, just to give you an example of what yours would look like, it'll be on your OneDrive. And if you've just created a 371 folder, it might be as simple as this, right? That would be the most simple way. If you just created one folder on your OneDrive, you put all your files in there, that'll always be your global path, okay? Now, that's not mine. Mine is down here, right? So I'm going to run this line of code, and you would run your line for whatever your folder is called. So I'm going to set the path. Now I'm going to open up that state cigarette tax data set, which we saved last class. So we originally had that state cigarette tax file. We had to import it because it was a CSV file. I then said if you want to save it as a .dta, now it's in Stata format, we can just kind of open it up. So moving forward, after last week, every file I'll start giving you will always be a .dta. So you can always just go to File Open, or the command that it'll kind of have is this use command. Okay? So we set that global path. I'm going to use or open that state cigarette tax.dta file. Okay? I can kind of verify, hopefully, that if I go up here to this like little grid with a magnifying glass, it now shows me, okay, I opened up this data. I've got a bunch of different variables for every state and in different time periods. Okay. So we'll go back to the program. We'll also have the do file opened up. We can kind of toggle back and forth. Let's see if there's anything I want to do here. I think last class I said, let's just keep the year 2000 just to make it a little bit easier. We're just dealing with 1 year of data. We could do it with every year, but we'll kind of continue this. So sometimes I'll do this so that when I'm running my code, I can see that it's actually doing something in Stata here. We summarized it. We created means, things like that last class. We're going to come down here where we left off, right? We looked at kind of this correlation last week or last class. I'm now going to say, okay, how can I look to see what the distribution of a variable is? So I'm going to go a little bit out of order here, right? So if I want to look at just a quick, dirty, like view of the distribution of the data, I'm going to use this hist command. Now, there's a way you can do this. You can go to like, I don't even remember where it's at because I don't use this very often. I think it's data, statistics, graphics. Histogram, I could then select the variable I want a histogram of. I wanted packs per capita, hit OK. We wait. Sometimes graphics take a little bit longer. Okay, it's not like the most continuous, but it kind of gives me an idea of what that distribution looks like. There's some kind of weird something going on here. I'm guessing this is like one state that really doesn't want people to smoke, so the taxes are really high. But it's pretty close to a normal distribution. Now, it's not perfect, but pretty close. So instead of using the interface to do this, notice when I use the interface, it still tells me what code it actually used. So here I kind of was giving you an example. So if I asked you to do this on a problem set, you could really just mimic the code I have here. This hist whatever variable, this is going to create that histogram. So you don't always have to go to that user interface if you don't want to. So if I were to run this line of code, hopefully, okay, produces the exact same thing. That's good. Okay. So I've got this original variable. What I'm going to do is use some tools that we talked about last class. So I said, anytime you want to use like a built-in function, right? If we just want to create a variable, we can use the gen command. So if I'm going to say I want to take, let's say I want to create the ratio of the pax per capita to population or something like that. I would say generate a new variable, call it var1, and it's going to be equal to pax per capita divided by population. But if I want to use these built-in functions, like I want to calculate the mean, so if I want to use this mean function, what it's telling Stata to do is go through every observation. How do you calculate a mean? Add up all the values for that variable, and then divide by the number of observations we had. Kind of similar to what you could do in Excel. You could take a column, you could use the sum function, add up every single value. You could then use the count function, gives you the number of observations, then take that sum of all the values, divide by the number of observations, that gives you the mean. Telling Stata, I want to use this mean function, it does all that behind the scenes. Okay?
Very good. I think it's
All right.
but the difference between gen and egen.
Yeah, so egen is using these built-in functions, right? So for example, let's say I want to create a variable called ratio, right? And I want that to be the cost per pack relative to the taxes per pack, right? There we go, divided by the taxes, not space, right? So if I just want to do some basic math, like I want to take this variable, multiply it by another variable, this variable plus 5, this variable times 1.5, add 6, right? If I just want to do some basic math or kind of take ratios or multiply variables by each other, I just need to use that gen command. So if I do that, I now end up with this new variable in my data set, which was simply taking that, where is it at? Cost per pack and dividing it by tax per pack, right? So you'll kind of see, this is kind of a weird thing. Like we get different ratios in different states, which is telling us that like certain states, given the price, they like don't all kind of have the same relative tax, right? Somewhere like the tax is a larger percent of the price than in others. So that gen command is if I just want to do like some basic math to create a new variable. The egen command is when I want to use these built-in functions. So if I want to calculate the mean, instead of typing out what exactly the mean is, there's a program built into Stata where it's all coded out already. We don't have to worry about doing that. It's just going to call that function. Okay. So when I use the egen, I want to create this new pax per capita mean variable, and I wanted to take the mean of pax per capita, right? That variable. So once again, there's a way you could do this. You could like do, what would it be? Data, create or change data, create a new variable, and you could go through all these lines. The interface, honestly, once we start using like the same things, it's just going to be easier to look at the actual code, right? But anything that we do, so like, we're at in time. I could do, now I have to remember what it is, pax per capita. And I want to create, where's it at? Position of variable specific, hit OK. Oh, I've already got it named. This is just to generate. Sorry, what do I need to do? I need to go to create or change, other variable creation commands. Might be this one. There we go. Once again, I don't use this very often, this because it does become like you've got to search through. So I take pax per, or no, sorry, generate pax per capita mean variable. I want to take the mean of generate variable egen function. Oh. Okay, what do I need? I need to take generate variable. I want the mean of, I think it would be tax per capita here. It does the same thing. All right. But now that gets like some weird things where we start to get things that don't really apply to us, like float. It can create different types of variables. So instead of using this interface, I'm generally just going to show you kind of the code that we would need just for what we're doing. The actual code might have different options if we do it all from the interface that we just don't need, and it kind of makes things a little more confusing. Once again, I don't use it very often. As you can see, it took me a while to kind of remember this, but hopefully by the end of the semester or by the end of these different modules or weeks, we'll kind of just have the code that we're ever going to need, right? So here, I want to use that built-in mean function. I want to create this egen, right? I'm going to use that mean function to create this new variable pax per capita mean. I'm going to take the mean of pax per capita. If I run this code, I look at my data. What did that do? For every observation, it just puts in whatever the mean of pax per capita was. So this is like the national average for pax per capita. Okay? I could then think about, go back to my do file. If I want to standardize a variable, we said we need to take every observation and subtract the mean. We have the mean now. But we also wanted to divide by the standard deviation. So the next thing we're going to do is use a built-in function, which is SD, standard deviation. And it's going to create a new variable that's called pax per capita SD. I'm shorthanding a lot of stuff here just so that we don't have like really long lines. And it's going to take the standard deviation of that variable pax per capita. So I'm going to go ahead, use that. Now I've got the mean and the standard deviation for every, like the national mean and standard deviation, but I've got it like assigned to every single observation. So what I would do by hand is for this state, I would take its value for the variable I'm looking at, pax per capita. I would then subtract the mean and divide by the standard deviation, and then I would put that value down. Go to the next observation. Take its pax per capita value, subtract the mean, divide. I don't want to do that by hand, right? So what I can do is I can use stata to say, okay, look, create this new variable. Well, now I'm not using a built-in function. I'm using some of the variables that exist in the data, which are pax per capita, the pax per capita mean I created, and the pax per capita standard deviation that I calculated. All I'm doing is kind of a general formula. It's not a built-in function. It's just a simple math form. So this new variable I'm creating will be my pax per capita variable, but standardized. I've subtracted the mean and divided by the standard deviation. Okay. So I'm going to go ahead and create this. Okay. I've now got that standardized value. Okay. So if I go back to last class and remember, we could calculate means and medians, right? Now, instead of creating variables, so I could look at the distribution. We could also just use that sum command, right? The sum command, if I run that, will tell me the mean and the standard deviation of that original variable. Okay. Now, the problem with using that sum command, if I don't create a variable, is this goes away as soon as I exit out of stata. Now, on the problem set, that's okay. Once again, there's multiple ways of doing the same thing. Just like I just calculated means and standard deviations, I could create new variables and then have those in stata, or I could use that sum command. But in your do file, what you'll need to do is, even though you have that code, you need to be able to identify, well, I need to be able to interpret this. Now, this seems very easy right now because it's like, well, duh, here's the mean and here's the standard deviation. As we progress throughout the semester, it's going to be less obvious like what the statistics from the tables we look like actually represent. And so here is where in your do file, if I was doing this for an assignment, I would probably add in a comment. So anytime we see this green text, we put a double backslash, that's a comment. It's not code that actually gets run. So in your do files, this makes it a lot easier for me to grade because this tells me, okay, here, the mean is what? 83 point, looks like 86, or no, 80. And the standard deviation is 26.08, right? So I can see your code that produced those results, and then you're telling me what those results were that you got from this table. But this table goes away, right? Now, I guess technically, if you wanted to, you could use screenshots and create this Word document where you're putting, using the comments, that way you could just have the code, have your comments, and just upload a do file for that problem set, right? So you don't have like multiple files and things going on. You can do this all in the do file using the comments, okay? Is that making sense what I'm saying? Are there any questions on that idea? If you have questions, they're not, no bad questions. We're just getting used to this, so. Okay. All right. So I already created this standardized variable. We looked at that histogram. We said packs per capita looked pretty normally distributed. If I standardize it, it should still be normally distributed, but what should its mean now be? If I subtracted the mean from every observation, the new mean should be 0. Right? I could almost think about this. Let me try to do one off the top of my head. 2, 4, 6, 8. Right? What would the mean of these 4 values be? So 10 plus 10, so 20 divided by 4. The mean is 5. Okay. If I subtract the mean from every variable, what are my new values? -3, -1, 1, and 3. What's my new mean? If I add these up, what do I get? 0. Very simple example to prove this to you. Obviously, like it's not a mathematical, like step-by-step proof, but we can prove ourselves to this with data. If I subtract the mean from every observation, the new mean I get will be 0. Okay. So this standardized variable, if I look at the distribution, it should still be normally distributed. Okay, once again, got a weird thing going on here, but pretty close. Now notice the values now aren't actually packs per capita, it's the standardized version. So if I have a variable and this packs per capita is below the mean, what will the standardized value always be? Well, if it's below the mean, when I subtract the mean, it will be negative. If I have a value and I subtract the mean, but it was above the mean, I will still have a positive value, right? That was true in our very simplistic data set, right? When we had a value below the mean, when I subtracted the mean, I had a negative value. For values above the mean, still positive, okay? Now, what should be the case in Stata, if I want to instead, and it tries to guess sometimes, so I'm pretty bad about typing. You'll notice it does this kind of nice thing. If I just hit tab, it tries to guess what variable I want. So it just saves me some typing. So that's kind of a nice, useful kind of tool in Stata to start utilizing. If I summarize this new, oops, I want the standardized version though. If I summarize that standardized value, we said the new mean should be 0. And if I'm standardizing it, we said it should give me a standard deviation and a variance of 1. So hopefully, if I've done things correct, when I summarize this new standardized variable I created up here, hopefully it has a mean of 0 and a standard deviation of 1. Now with small data sets, it's not going to be quite perfect, right? So when I see something like this in Stata, what this is telling me, the way that we read this like scientific notation, negative 1.18 times 10 to the negative 7. So anytime you see like an e to the negative, that means take the decimal and move it 7 places to the left. So this would be what? 0.0000001. It's essentially 0, right? When we start to work with extremely large values, so let's see if we have one in this data set. We might have to hold off until next class. I want to get rid of this. Let's look at tax revenue. So I can type things in my do file. I can also just do it in the pro. So let's look at tax revenue. I summarize tax revenue, I could also see a number e to the positive. So what does that mean? Take that value and move the decimal 8 places to the right. So this would be like what? 1 0 0 0 0 0 0 0 0. So I have what? 8 zeros. This would be what? $100 million of tax revenue would actually be what this represents. So a lot of times when we look at these tables, they'll give us values, and if they're extremely large, it's going to say, okay, 1.63 is the mean, but move the decimal 8 places to the right. Okay, so this is actually not 1.63. This is, like I said, what, 163 million, right? And then this wasn't negative 1.18. It was negative 0.0000001, or essentially 0, right? So with these small data sets, even when we standardize the variable, we won't end up with it exactly a mean of 0, but it'll be really, really close. If we had much larger data sets, what we would end up here is an exact mean of 0, right? It's just that with discrete data and kind of small data sets, it might be a little bit off, right? But it's going to be very close, right? Any questions on this before we keep moving here? A couple minutes and we'll kind of get out of here. So just to kind of make a point, if I look at that standardized variable of PAX per capita that I standardized, so I know I've got the mean and standard deviation of 0 and 1. What is the minimum value? So that's the observation that had the lowest PAX per capita. How many standard deviations below the mean is that state? Well, if it's negative 1.99, once I standardize the variable, the units are no longer the number of packs smoked per capita. The units are now standard deviations. So the lowest state has an average of 2 packs per capita below the mean, right? Or the number of standard deviations below the mean would be about 2, right? Negative 2 would be negative 2. We do 2 standard deviations below. Now, the highest state in the data is 2.77. That means the highest state in our data set would be 2.77 standard deviations above the mean. Okay? So once we standardize the variable, the interpretation, the units are essentially the number of standard deviations away from the mean. Okay. Which once we've standardized it, kind of makes it nice and easy because the mean is essentially 0, right? So it just represents standard deviations. So that goes with, where are we at? Kind of standardizing these variables in Stata. We'll kind of pick up thinking about distributions, talking a little bit more about, I can go back here, Z tables, how we use those. I think I had it set to be week 2. We didn't get quite as far as I thought we might last class. So we'll import a different data set, which is selection data. We'll then kind of start to think about creating conditional means, some of the stuff that we talked about today, just doing a little bit more of it in Stata. So we'll kind of start out with that and then transition back to the slides where we start talking about the standard normal distribution, looking at the Z tables. When it comes to actually practically using this later on the semester, we won't be like using those Z and T tables near as much. Right? We'll use them a little bit, but a lot of it will be kind of getting from Stata. We don't actually have to physically use them. It'll spit out at us those probabilities, or what we end up calling things like p-values, right? We can get those directly from Stata without having to actually hunt through these physical tables, okay? So we'll kind of pick up in this do file where we left off today, using that new data set. We'll then kind of go back to the slides where we start to then revisit this standard normal distribution and eventually what we call the student t distribution. Okay? So once again, you can get a little bit further in that problem set. So make sure you've got Stata working. If you don't, reach out to me via email, or it'd be a good time to stop by office hours. Look for that announcement about the additional office hours this week. Other than that, if you didn't celebrate enough last night, have fun celebrating last night's victory, and I will see you guys on Thursday. Okay?